Solid design principle. Solid design principles. So we have discussed all the solid design principles from single responsibility to open close to liskov substitution, interface segregation, and dependency inversion. Okay, now it's time that we kind of do some kind of inference stuff. So in solid principle, we start with the single responsibility. So if there is a class and class has data attributes and it has operations, then all the data attribute and operations should have single reason to change. Okay, so the C++ class, we can match it to machine learning classes also. So in machine learning, we have set of classes and against each class. So generally what we do is that in machine learning there is a data set, and inside a data set there are features. It can be matched with the attribute, and with certain combination of feature data, okay, we say that this belongs to a particular class. With certain combination of other feature data, means if it has a like iris data set, sepal width, sepal height, and then petal width, petal height. So for certain range of sepal width, sepal height, petal width, petal height combination, we say that this belongs to which class. Then certain combination we say this belongs to which class. So in a class, if I have a class, then in a class we have operation and attributes. If we have operations and attribute in a class, then there should be only one reason that they would change. There shall not be two reasons to change. If there are two reasons to change the data and its operations, then better to segregate, better to divide into two different classes. Okay, like if I leave the machine learning right now and come to normal example, like we gave example like a printer. Printer is a class and it has a data and data features or data member as like collecting the document and printing it. So collecting the document is completely separate set of operations than printing it. So collection has nothing to do to print it. So collection would vary on its own in a sense that we can provide a new kind of methods, new kind of data structure while we do the collection of the document. Okay, so like document collection procedures or the document specification and document kind of formatting. So all these will fall in collection of the document. So that is completely separate, and printing is completely different. I mean, they have nothing to do. So they would vary. So if someone wants to give for printout, then he would send a document with a different kind of formatting. But finally, whatever formatting it set, then finally it will come as a PDF that will go for printout. So the finally when it goes to printout, the formatting is common that will come in PDF. So receiving the document in a certain set of formatting and then doing some generic formatting and sending into the printer. So they are completely different. I mean they have no reason to kind of share anything. So if this kind of scenario happens, then generally we take it out and we create two classes. So one class is for data collection and formatting, and other class for document printing. So whenever we have class and inside class there can be many groupings and each group has different reason to change, okay, based upon the changing scenario, then it is nice to have kind of single responsibility and one class can be divided into n number of classes. The way like iris data set we said in the machine learning. So one set of features. So there are only four features: sepal width, sepal height, petal width, petal height. But a particular So the iris can be of a different category, setosa, versicolor, or something like that. For one set, okay, so one kind of flower of the iris, the combination of these features, sepal width, sepal height, petal width, petal height, they vary differently. For another iris flower, these four feature combination of these four feature, okay, so all the data samples which will have this feature value, they vary separately in a, okay, so in a different way. If there is a third type of iris flower, then all the samples as per these four features, they vary separately. So there are three classes I can say that iris database in machine learning generally we carry, because there are three reasons that their data samples would change. So there are three regions, so three groupings, so three classes. Like printer, here we say data collection formatting is one area where it would change, and printing is one area it would change. So we come to something like orthogonal characteristics. If in a class, if there are two subclasses and they are orthogonal to each other, or there is no co-multilinearity, this is also a term is being used, then we say that soribus means we cannot live together, not required. So in this fashion, we go for kind of making it two different classes. So this is kind of single responsibility. Each class should carry one responsibility, not two or more responsibilities. So all the methods in a class should be cohesive. Okay, like LDA, linear discriminant analysis, we talked. So that in machine learning, where we kind of when we get when we receive the data, then interclass cohesion we increase. Sorry, intra-class cohesion inside a class, the cohesion between the data samples will increase, and interclass, okay, the separation, the reason to separate, that will increase. So interclass separation will increase, intra-class cohesion, okay, the bindness that will increase. So we get separate clusters, okay, logically far apart from each other, and inside that all the samples are together. So all these are scenario where we go for single responsibility. One class should carry all the data members should be cohesive. So this is single responsibility. In design patterns, we saw command design pattern that comes as single responsibility. Like if we have a robot, and robot has four operations: move left, right, and forward and backward. We can have a command abstraction where we have four different commands. Okay, so command move left, move right, move forward, move behind, and all these four commands, they share the abstraction, the interface as command. Command is a robot is a class which has a left, right, front and back as functions. If I call those functions, robot would move accordingly. This is robot. Now we have a command class new. From the command, we have four commands that is derived. That is move left, move right, move forward, move behind, and they have the robot as their containment. And move left, so they have only one operation called execute. So command interface has one operation called execute, and left, right, front, backward, these classes, they override the, or they realize the execute virtual command, and inside that they do whatever they want to do. So like if I call left command and say execute, it will move left. So this way we have four different commands because they have separate responsibility. And now we can push all these command instances in a list. And we need to do is in a list we can just keep popping out the list and say execute, execute, execute. So this is the scenario that we saw in kind of uh, in single responsibility. If we move to open solid open close principle, then open close principle is something that whatever the change we make in our class, okay, so that should be done. Once we have made the changes, once our function is done, once our class is done, okay, making all the kind of when we are done with making all the kind of modifications, then it should be closed for modification. Once we have finalized the function, then we should not touch the function again. Once we have finalized the class or module, we should not touch the class or module again. So it will become like a rock. Okay, so developed class or developed function, developed module, it should behave like a rock. Okay, closed. If it is closed, then it cannot be further modified. If that is the scenario, if someone needs to kind of make changes, then he can extend it. Okay, if he extends the current closed class, then he can add methods, or he can override a method, or he can use a method. So this way it can be used. So this is kind of open closed principle, open for modification, open for extension, but closed for modification. Okay, so this is a crucial a design principle, and it is heavily used in Python nowadays as a like a decorator design pattern. So decorators are extra functions which take the closed functions as their parameter, and then they write wrapper over it. So if I have a already written called function called func, and it is passed to decorator called deck, then deck would receive func as parameter, and it will do whatever it wants, then it will call the func. Okay, so this way also through containment also we can extend, so through inheritance and through containment. So decorator is also a design pattern, so that falls under the structural design pattern. So once we can extend we can kind of extend the functionality of uh, any class that is following open close principle through decorator design pattern also. That also we saw. Then we forwarded to liskov substitution. So liskov substitution comes to a kind of stage where if I have a pre-written class and code has written, so there is a kind of a client. Okay, so there is a client which depends upon my class. So depends upon my class in the sense it has written its algorithm based upon my class methods. Now, if this is client class, this is the utility class or service class. This is a client class, this is service class. Client class depend upon the service class. So, based upon the service class methods, it has written a full algorithm calling this method, that method, or whatsoever. Now, at runtime, if so, the service class has now I extended it to. So like there is a kind of a class called vehicle. Okay, so vehicle, now it is that go to fuel station. There is a function called go to fuel station. Then okay, or make the get the fuel. So get the fuel, then start the engine. Start the engine. Okay, then take brake, take accelerator, take a okay, use steering. So these are the function inside the vehicle. Now someone has written algorithm based upon the vehicle functions. Now tomorrow a vehicle came as car. Okay, so if someone replace the car object against the vehicle pointer, he should be able to do that completely. So whatever code is written taking base class pointer as the scenario, and any new derived class comes into the picture, it should completely substitute the base class. Okay, so that is a liskov substitution. Like I started with a vehicle as a get the fuel, start the engine, take brake, take accelerator, and then okay, use the steering. Now vehicle can be car, again inside, again I can derive from the car as petrol car, diesel car, electric car. So get the fuel means electric car would go to the electric fuel station, it will take the fuel, that is electricity, and then everything is same. So this way, a liskov substitution is now, if I had written the program through kind of a vehicle interface pointer, then I could, now I can substitute a car. Now even I can substitute electric car. So that is two line down in the inheritance tree. Okay, but if I have put in the vehicle class, if I have put a code like method like get petrol or get gas, then it is not following liskov substitution, because now I cannot I cannot have a subclass as electric vehicle, okay, or electric car, because electric car is will not get the gas, it needs electricity. So when we design the base class, we should have the abstraction functions, the methods, in a way that whatever the derived class comes into the picture, wherever the base class is used in the client side, wherever the base class is used, the derived class should exactly fit over it. So this is a liskov substitution. If we see the design pattern like iterator design pattern, or well, global strategy design. So in iterator design pattern, an iterator is a friend class to many kind of lists, like list, set of set many kind of containers. There is an iterator, it iterates through a container class which has which is of many types. They contain either list, or they contain multi-set, or they contain a kind of other kind of data structure. But if someone is using iterator design pattern, he is using iterator methods to iterate the all the type of possible container. Inside the iterator, it knows how to iterate them. So it is only possible when kind of so if iterator is an interface. From iterator interface, we have actually concrete objects are list iterator, or map iterator, or set iterator, whatever. Everyone is following the iter methods. So if I have written code with the iter base class interface pointers, then any of object would work. So idea is that, so there are two kind of scenario. One is iterator and its tree, and the container classes. There are so many container classes. So iterator is friend of container, and iterator provide a set of generic methods. Those are realized by separate iterators. My code is written with the iterator pointer. Doesn't matter which object comes into the picture. So now whatever the container, okay. Now if I have iterator, so I have written the iterator with the code. Any new iterator comes into the picture, list iterator, map iterator, set iterator, hash iterator, whatever in the actual code, they should exactly substitute wherever the iterator code with the iterator is written. Okay, so if someone has written its code with iterator pointer and new iterator subclass object comes into the picture, it should exactly substitute the iterator. Okay, so this is a liskov substitution principle. Now then we have kind of LID. So IDI is a interface segregation. So interface segregation